Okay, so today Neil will be talking about our work in crash-proofing the HDF5 library. I'm just going to start off by talking about the release for just a minute. So originally we had planned to do the release last Thursday, and unfortunately this was slightly delayed due to um, the late arrival of an important security patch from Amazon. So we've merged that in. We're going to give it another week or so to to bake and to be tested, and we'll do the release on April 11th. So that's next Thursday. So sorry about the delay, but nobody's really, I think, championed. I think people would rather have the security fixes than wait 6 months for them. So and with that, I will give it over to Neil.
All right, thanks, Dana. Today I'm going to be talking about a new feature that we've designed and would like to implement if we can find some funding for it. It's basically we've been calling it crash proofing. So what it is it's a feature that you can turn on and it will cause metadata rights to be logged to a write-ahead log in such a way that if the application that's running that's using HDF5 crashes for any reason, it could be a bug in HDF5 or a bug in the application, the kernel could crash, or someone pulls a plug, or there's an earthquake or anything, that you can still go back in and see the HDF5 file and the log file and still be able to recover a consistent state of the metadata within the HDF5 file. And how recent that consistent state is guaranteed to be is configurable, and we also will also add a facility to automatically restore the HDF5 file to that consistent state. And this feature is designed to be easy to use and have minimal overhead, and we have some benchmark results that show that. The majority of the overhead we found comes from the need to sync the file when we well, I'll talk about it later, but most of the overhead is kind of unavoidable, I guess is what I was saying. And so we're only targeting metadata because raw data is already if you look at the reference manual, the documentation, there's already we already specify pretty clearly exactly when the raw data that you write actually hits the disk, modulo any page buffers, but you can turn those off. And also we want to keep the overhead minimal and the size of the log file minimal, at least for raw data heavy workloads. And so, so we've implemented, or we've designed this write-ahead log where basically all metadata rights that would hit the file are instead written to this log file. They're just appended one by one to the log file, and then every once in a while you can have a log flush and a log checkpoint operation. A log flush is an operation that takes all the dirty metadata in the metadata cache in HDF5 and flushes it all to the write-ahead log file. And then it puts a marker in the write-ahead log file stating that this is a consistent state that you can restore to. And if you restore to all this metadata that's been logged to the HDF5 file, then all the pointers will be correct. Everything, there won't be any dangling pieces of metadata or anything in an inconsistent state. Whereas if you just restore to any arbitrary metadata location, that might not be true, because we don't want to get into the difficulty of maintaining flush dependencies and everything with Swimmer that has made those implementations difficult, and also add more overhead, because we're not trying to, this isn't trying to implement full Swimmer for the library. It's only trying to add the crash proofing facility. And then, so you have log flush that that flushes to the log file and marks it the state is consistent, and then you have the log checkpoint, which it basically takes everything that's been logged to the log file and writes it to the HDF5 file, and so it creates another consistent state, but it creates a consistent state in the actual HDF5 file. And then we haven't decided if we want to do this, but I think probably what we would do is just truncate the log file, just start over. Once we've verified that all the metadata has actually been synced to the HDF5 file. So that's called a log checkpoint. We plan to have configurable sort of intervals for both of these. So a log flush is how often you want to be able to have a consistent state, and a log checkpoint is how often you want to clear out the log file. And the main reason for clearing out the log file, I think, unless someone else has an idea, I think it's mainly to keep the size under control. So it might make sense to have like a time-based interval for the log flush and like a bytes written type interval for the log checkpoint. But I think we plan to allow both intervals for both logs. And also, this could also be up for debate, but right now we're thinking that we would have HDF flush. If you call it on a file that has the write-ahead log enabled, it will invoke a log checkpoint. So I'll write everything to the HDF5 file. And so yeah, like I said, it adds a marker to the write-ahead log for the log flush. And if we decide not to truncate the log file, then it will add a different type of marker for a log checkpoint. So that means when you're doing the restore operation, you start from the latest log checkpoint and run to the latest log flush, and you throw out everything after the latest log flush, because anything after that might not be consistent with respect to the other metadata in the file. So here's a little diagram for how this plan to work. So anything that comes in that results in metadata writes to the metadata cache. If the cache needs to evict something and the wall is enabled, then it writes for the metadata to the log, and then writes to. We're planning to access the write-ahead log through the existing HDF5 virtual file layer facility. So that will allow the flexibility to have different ways of accessing the log file, which will be especially useful in parallel because the log file needs to be visible to all processes in parallel. And then if you explicitly call H5F flush, then if the wall is enabled, then it skips the metadata cache and just I guess this document doesn't mention that a wall flush it needs to do a log. So an HDF flush invokes a log checkpoint, and first step in a log checkpoint is to do a log flush. So it will actually write things to the wall first. But this is kind of a simplified diagram. So it'll kind of, once it gets to the actual flush to the file section, it'll skip the metadata cache, and it'll just basically read everything from the write-ahead log. Well, first it'll flush everything that's in the metadata cache to the file, and then it'll read everything that it needs from the write-ahead log, and then write those to the file, and then it'll be done. So one sort of difficulty with this is, so if you evict something from the metadata cache and it hits the write-ahead log but not the HDF5 file, and then you need to read that back into memory, then you need to know, don't read this from its address in the HDF5 file. You need to read it from a different address within the write-ahead log. So we're planning to internally implement these sort of stub entries in the metadata cache that say this item isn't in cache, but if you need it, then you need to go to this location in the log file instead of the HDF5 file. And we also need to be able to keep both the stub entries and the regular entries around, or have some sort of way of having the regular entries maintain the log file address for pieces that are flushed from metadata cache to the log but not evicted. So there are a few different cases we need to keep track of there, which is, can be a little could get a little difficult, but I think it should be manageable. We have some design decisions to make sure that's as maintainable as possible while still being performant. But I think they're not won't be too difficult. And then we have another little wrinkle where, so if you write a piece of metadata, so let's say there's a log flush, and then after the latest log flush, you write a piece of metadata, and then another operation deletes that piece of metadata. It could delete part of it, or it could delete the whole thing, doesn't matter. And then you write some new raw data, and then that raw data gets put into that section of metadata, which, depending on the aggregator settings, that might not be possible, but in some cases it could be possible. And then you have a crash before you get another log flush. So then what happens is, then when you go to recover, you go back to the beginning and you replay all the metadata, but you don't replay any of the raw data. So it will replay this metadata write, and when it replays that metadata write, you go down here and it'll overwrite the raw data that you wrote in this section. So while we don't make guarantees about raw data consistency with this feature, we don't want to sort of undermine the existing semantics about when raw data hits the disk that already exists, and we don't want to overwrite raw data that the user could reasonably expect would be visible. So right now, I think the plan is to just delay recite. So you can delete metadata here, but we'll just hold on to that deleted section, and we won't add it to the free space manager until you get to the next log checkpoint, the next log checkpoint. And that should prevent this from being an issue, because then you won't be overwriting raw data. You won't be putting raw data into this section until you get to another start point for recovery. Another thing to consider is for variable length and reference types. The variable length data array is considered metadata. So that means that it will be included in the log file. And so maybe that's great because it'll be sort of made consistent, but it also means that it could, if you have a lot of variable length data in your file, then it could cause performance issues. It could cause the write-ahead log to be very large, and depending on your settings, it could cause frequent log checkpoints. So that's something to keep in mind. We're planning to, if this is something that people are concerned about, we can add an option to exclude these types of global heaps from the write-ahead log. So that would mean that there's no guarantee on the consistency of variable length data, but it stops them from being a performance liability. Also, similarly, attributes and compact data sets will be included in the write-ahead log, but I don't expect that to be as big of an issue because those are generally very small. And so, so that we're planning to create the log when we open the file, and then after we close the file normally, or if you reopen it and it does the recovery, but the reopen was with the wall disabled, then we'll delete the wall after it's no longer needed. So it's sort of like one of those files that end in a tilde or start with a tilde and from MS Office or something like that. Yeah, so we definitely want to target parallel with this, and it should be reasonable. We shouldn't need to do any extra coordination because the way HDF5 works in parallel is all processes have the exact same stream of dirty metadata. So everyone will know so only process 0, at least initially, will write to the write-ahead log. But all the processes will know, they might not know, well, yeah, no, they'll know which pieces of metadata have been flushed to the write-ahead log, and they can do all the same calculations, and they'll know the exact addresses that they get flushed to in the write-ahead log without having to do any coordination, because they all have the same stream, and they all use the same algorithm to determine which pieces get evicted in which order and things like that. So they'll know the addresses to add to the stub entries to know where to get those entries from if they need to read them from the write-ahead log. So in the page buffer, metadata accumulators probably don't really apply because we're not doing much metadata IO to the actual HDF5 file. The page buffer could apply to raw data. And they could also apply for potentially for reads of metadata from the HDF5 file, from very stale pieces of metadata, and they would also change the method for running log checkpoints, though I don't expect they would really have much benefit in that case, because you're just kind of adding a cache to like just kind of a big dump of all the metadata. And one thing we can also speed up the metadata, like the flushes and checkpoints, by packaging up all the pieces of metadata into like a single operation and passing it through the vector write routine, and possibly the vector read routine for the checkpoint. We're going to talk about compact data sets, file format. So we sketched out the file format for the entries. So here are the new API functions that we've designed. The set wall to enable the feature, and then the different interval types in interval values, and then the access property list for the log file itself, which is only used for the file driver. Then the getter for those properties. Then the auto recovery. So this, if you enable this, then if it determines that the file was closed incorrectly, then it will try to automatically recover the file, and we can use a field in the file superblock to determine whether it's been closed correctly. And then also the HDF wall flush, which initiates a log flush manually, instead of relying on the automatic interval in the setter routine. So the recovery process, so I sketch out the algorithm for the recovery process here. So yeah, basically run from the most recent log checkpoint marker, or maybe from 0, and then basically read each entry and write the logged entry to the correct offset in the file. Then stop as soon as you get to the most recent log flush marker, which means that you do have to scan through the file twice to find the most recent log flush marker, but we think that's okay because we're not really optimizing for recovery speed. We're optimizing for minimal overhead of creating the log file, because we don't expect it to need to be used very often. And then trim the log or delete the log depending on whether it was reopened with all enabled. Then if you're open with read-only access, it's slightly different. Do the same. You read all the entries, but because you can't recover the file because you're open with read-only access, you just create all the stub entries you need to be able to access the file in the metadata cache. So you're just building a consistent state in metadata cache with the stub entries, so that you can read the file, although you won't actually recover it. So the next time you read it, you'll have to do the same thing. And So we go to sort of specifics about how we plan to implement it. I guess running low on time here, but I wanted to get to we ran sort of the benchmarks where we sort of tried to mimic these operations, and we're still kind of ironing out a few kinks, so they might change a little bit, but basically the takeaway is the majority of these, so we did 2 metadata heavy benchmarks and 1 raw data heavy benchmark, and so we did CPU time and wall time for different intervals, and also for ones that never did the checkpoint, for ones that did do the checkpoint. And so the takeaway is that if you don't do the checkpoint, then it's very minimal overhead in every case, basically. So these orange and blue ones are the metadata heavy benchmarks. So you can see it's like, yeah, so some of these are like up to 60%. Most of them are a lot smaller, especially for the larger intervals. And like I said, these are basically benchmarks. We're just creating a bunch of empty or very small data sets, things like that. And then if you don't do the checkpoints, then it's very minimal. One thing that we found, sort of looking deeper into the numbers, is that most of the overhead actually comes from not logging the metadata. It comes from when you do the checkpoint, you need to do a sync on the HDF5 file, because you can't delete the log or proceed with the marker in the log until you know that everything is in the HDF5 file. And that sync it turns out to be somewhat expensive, even though it comes out of what you have to do at the end. For whatever reason, just doing multiple syncs is more expensive, at least in Linux. And so yeah, we found basically 0 overhead for the raw data, and then a little bit more for the log checkpoint. And again, that comes from doing the occasional syncs. In this case, it's because there's a sync at the end. And I think we need to add a sync at the end for this one too. So this may go up again, but again, this is because we're guaranteeing consistency, so we need to do file syncs occasionally. And so that adds like 2-3% overhead. Yeah, so I think we have 5 minutes left. Is this a half-hour meeting? But yeah.
Questions. There are questions.
I have a
sure.
million pieces of feedback too, Neil.
Okay.
Is it time for questions, or because
That's up to Lori, I guess. I think there's at least 5 minutes for questions.
Yeah, so we have time for questions. And Dana, do you kind of want to organize and be the moderator here just to maintain our time limit?
Yeah. Who wants to go first?
Me, of course.
All right, go ahead.
Okay, Neil, thank you. Looks like it's nice document, but just aside from the question, it was impossible to follow. My screen was jumping all the time, so I couldn't, so next time maybe scrolling, maybe having few slides will do much better job in terms of idea. But since I'm familiar with idea, the first question is, on one of the first pages was that you compared performance with metadata journaling. Which project you're talking about? The old one from Sandia's time, or a new part of VFD Swimmer?
We were looking into the very old one.
Okay. Which is probably true. The next question is, did you compare your solution with existing one where you just need to write a tool? Because VFD Swimmer, I believe it's kind of misconception. It has 2 parts. It has a reader, which is VFD, and it has modifications to the library that writes this metadata journal, and how it performs already implemented solution, what you're proposing. And follow-on question about, and that will be my last, will this approach work on NFS, where it is the biggest problem? So have you compared with existing solution to which you just need to write a tool? This is part of VFD Swimmer, or and how
we will look at VFD Swimmer, Elena.
Huh?
We will look at VFD Swimmer.
I mean, I'm welcome to. I'd be happy to send you our benchmark parameters if you want to try to run some benchmarks with VFD Swimmer.
Okay, so you didn't run your solution against existing one. That's
We haven't tried VFD Swimmer.
okay. Okay.
We looked into it, but we haven't tried. We haven't tried to run it.
That would make a lot of sense,
And
sending them to Elena.
will your solution work on NFS?
I would need to look into it to be sure, but as long as a file sync operation isn't lying, then it should be fine, because we rely on when we put the marker in the log file or we truncate the log file, we rely on the syncs indicating to us that everything is actually in the file system. So, and I believe the file syncs on NFS will tell the truth, but I am not an expert.
I think NFS only gives you close to open consistency guarantees. You may need to double check harder.
Yeah, you have to close the file. That's what we learned. But yeah.
All right. Well, I'll have to look into that. I suppose we could add an option to close and reopen the file, at a low level and without, messing up the internal state of the HDF5 structures. So it should, in theory, be possible, I think.
You should be able to probably embed that in the flush or truncate or whatever callback in the VFD. Just say, well, sorry, this is the way it's supposed to be.
Yeah.
Still had any questions and comments.
I don't know if we would want to always do that or try to detect if it's on NFS or just rely on the user knowing and setting a property.
It's possible to detect when it's on NFS. There's code in Romeo that does that.
All right. Yeah, we'll have to look into that.
Yeah, it's something we thought about adding for swimmer tests to just not run them when they're on NFS. People report problems that aren't real problems.
But
okay, so
you don't.
50. So go ahead, Neil.
I was just going to mention that we don't rely on right ordering in the way that Swimmer does, so it should be a lot easier to get to work on NFS.
Right, exactly.
And this is not ordering, it's the matter of things being in the file written.
Right. That's right, yeah. As long as everything is in the file when we finish our, whatever sync means to us, then it should work. It doesn't matter what order it hit the file in.
And on NFS, you have to close the file. So at least what we learned. But you were going to look into that new Swimmer implementation. Did I understand you correctly?
In the VFD Swimmer?
Yeah.
We are going to try not to spend much more time on this until we find funding for it. So we're just kind of presenting our design in RC right now.
Because there is implementation already, and you're designing new thing.
Yes, we are aware.
Okay. Okay.
Right. Yeah, like I said, we can send you
every time you bring this up. You mention it. Yes, we know.
There's a bunch of details here. I could help you fill in places here and gaps for implementation, but we're out of time.
Yeah, we need to get going. But yes, we should do that.
All right. Yeah, I'm happy to talk to you sometime.
Sure.
And
okay, thanks.
You will send RFC around, right?
Yeah, we're still trying to get there are some parameters on the benchmarks weren't quite right, so the numbers may change, but they should be in the same ballpark. For the most part, very small, especially if you don't do occasional log checkpoints.
Do you want commentary and discussion before you send it around or after? I don't care either way.
I can meet with you if you have some time in the next couple of days, I suppose.
Sure. Yeah. I mean, really up to you. Okay.
All right. Yeah, I'll talk to you offline.
Okay, cool.
All right, thanks for coming, everyone.
Thank you all.